Good evening, everyone. Let us start with today's class. So this is the week 11 of the online interaction session for Aspen plus simulation software. It is a course which is offered by Professor Praveen Kumar Shah from the Department of Chemical Engineering, IIT Guwahati. And my name is Rajdeep, and I am currently pursuing my PhD from Department of Chemical Engineering, IIT Kharagpur. So the first problem that we are going to solve today is a rat flag problem. So a feed mixture which is specified in figure 3.1.5, that is over here it is being specified. It is to be distilled by rigorous rat flag model. The column consists of total 24 equilibrium stages including condenser and deboiler with a stage pressure drop of 2 kilopascal. Consider the condenser, a total pressure of 125 kilopascal, and the top stage, stage number 2, pressure of 130 kilopascal. The distillate flow rate is 120 kilomole per hour and the reflux ratio is 2. A side product is withdrawn from the 14th stage. Now we have to apply SRK property method, that is Swab-Redlich-Kwong property method, to simulate the column model and report the product compositions. So take 5 minutes time and try to solve this problem on your Aspen. After that I am going to solve it from my side. So the components are benzene, toluene, and diphenyl. So let us specify the components: benzene, toluene, and diphenyl. The method name is given to us. So the method name is SRK method. So selecting the SRK method from the method name. The interaction parameters are updated. Now we are going to run the property analysis / setup. Now coming to the simulation environment. So the column that we have to choose is rat frac. So we have one feed, then we have distillate, we have bottom, and here is one side product. Let us rename the streams. This is F, this is T, this is S, and this is bottoms B. Now first we have to specify the feed specifications. So the feed is at 110 degrees Fahrenheit. So this is 110 Fahrenheit. The pressure is 175 kilopascal. So this is 175 kilopascal, and feed stage is 10th. Okay. And the mole flow is given in pound mole per hour. So selecting from here pound mole per hour. So benzene is 250, toluene is 80, diphenyl is 10. Next, coming to the rat frac column. In the rat frac column, it is given that the column consists of 24 equilibrium stages. So number of stages is 24. Total condenser is given over here. Condenser, total pressure of condenser, top stage. The distillate flow rate is 120 kilomole per hour. So distillate flow rate is 120 kilomole per hour, and the reflux ratio is 2. Now going to the streams. The feed stream, it is given its 10th tray above stage, and the side stream is withdrawn from the 14th stage. And this phase, it is vapor. Let the side product flow rate be 50 kilomole per hour. Let us give it as an initial guess. So now the pressure is required. The condenser is 125 kilopascal. Stage pressure drop of 2 kilopascal. And the top stage pressure is given as 130 kilopascal. Now it is given that the required input is complete. Now we are going to click on next and we are going to run the simulation. So what was asked from us in the problem? In the problem it was asked that you have to simulate the model, column model and report the product compositions. So the product compositions that we have are D, S and B. So from the results we are going to go to streams, and this is B, D and this is S, and the product compositions. So these are the product compositions for the product streams. So this is the answer. So there is just one small modification in the problem. Here, let me add it. The side product flow rate is 10 kilomole per hour. So let us save this problem. So in this next problem, what we are going to do is we are going to solve for Aspen dynamics. So the first problem that we are going to do is we are going to solve the dynamics of a distillation column. So the problem states that the simulate and control a radfrac column, and the simulation has to be based on these data. The feed flow rate is given as 100 kg per hour. Water is 55% mass fraction and ethanol is 45% mass fraction. The temperature of the feed is 40 degrees Celsius. The pressure is at 6 bar. Total stages is 18. Stage 1 is the reflux drum. The pressure is given as 1 bar. And stage 18, it is the reboiler and the pressure is given as 1.5 bar. The feed stage is at 9 stage. The pump pressure is 6 bar and the control valves will be present. So the pressure change across the control valve is 3 bars. The thermodynamic model that we have to use is NRTL. The reflux ratio is 2 and the distillate flow rate is 45 kg per hour. So we have to perform the following control actions. First is we have to control the reflux drum by manipulating the distillate flow rate using a proportional controller. Then the base level is controlled by manipulating the bottom's flow rate, that is also a proportional controller. Then we have to control the pressure by manipulating the condenser heat removal. It is the using a proportional integral controller. Then the reflux flow rate is fixed, and then the feed is controlled by a uh, proportional integral controller. So this is the overall schematic of the process flow diagram that we have to simulate. So I'm giving you 5 minutes time. Just simulate this process flow diagram. All the data and details is given over here. I'm going to do the simulation as well as the dynamics part.
So there is one confusion. In the problem statement, it is mentioned ethanol. In the simulation screen, it shows methanol. So which one we should use, sir?
Hello?
Yeah, sir, can you hear me?
Yes, I can.
Yes, sir. Sir, the problem page, na, sir. There it is mentioned as ethanol, and the current page shows as methanol. So which one we should use, sir?
Use methanol.
Methanol. Okay, sir.
So we have two components over here, ethanol and water. The property method that we have to use is NRTA. We are running the property analysis. Next we are coming to the simulation. So coming to the flow sheet, we have one red flag column, then we have two pumps, and we have three control valves. So let us rename this as control valve 1, the column as C1, this is pump 1, this is pump 2. So this is the feed, it is entering this column C1, the liquid distillate is going inside the pump outlet is going into the control valve 1, and then we have our product. Similarly for this stream also, let us rename this. This is stream 1 S1, this is the feed, this is S2, this is S3, this is the distillate D, this is S4, S5, and this is the bottom B. So we have these blocks. Now our flow sheet is complete. We have to specify the feed stream. So this is the S1, that is the feed stream that is coming in. So the feed stream, it is at a temperature of 40 degrees Celsius and pressure is at 6 bar. So 40 degrees Celsius and the pressure is 6 bar. The flow rate is 100 kg per hour. So converting it into moles, into mass, 100 kg per hour, and this will be in mass fraction. So methanol is 45%, 0.45, and remaining is water. Now the feed has been specified. Now going to next, we have to specify this is if I, this is control valve 2 and this is central valve 3. Okay. So we are coming to the column specifications first. So the total stages is 18. The condenser is total condenser, and it is given us that the distillate flow rate is 45 kg per hour and the reflux ratio is 2. This is 45 and the mass ratio of the reflux ratio is 2. Now coming to streams, the feed stage is 9th. This is 9, and coming to pressure, usually what we do is we give the pressure of condenser and stage pressure drop or stage 2 pressure, that is the top or bottom pressure specifications are being asked. Instead of doing this, we are going to give a pressure profile. So stage 1 is given and stage 18 is given. So the pressure for stage 1 is given as 1 bar and for 18 stage it is 1.5 bar. Now we are going to click on next. So we have come to control valve. So in the control valve it is said that the delta P or the pressure drop is 3 bar, and we are handling liquid feed on liquid phase. So we are going to use liquid only. So the pressure drop is going to be 3 bar. We are going to click on next. Similarly for control valve 2, this will be liquid and the pressure drop is 3 bar. Similarly for control valve 3, the pressure drop liquid phase and the pressure drop is 3 bar. Next we are coming to pumps. So for pump, it is given 6 bar. So the discharge pressure, it is going to be 6 bar for pump 1. Similarly for pump 2, the discharge pressure, this is also going to be 6 bar. Now it is said that the required input is complete. Now we are going to click on next and we are going to run the simulation. So the results are available. We are going to go and check the results for column 1. So these are the results. You can see that the pressure is varying. Okay, now what we have to do, now over here we have to do the dynamics. For dynamics, the first thing that we need is we need a few dimensions of the column. So how are we going to do that? For that we need the hydraulics or the flow rate at which all of these components are getting out, or the tray hydraulics of the entire radfrac column. For that we are going to go to setup, and over here it is an option of design and specify column internals. We are going to select this. It is going to say that this simulation is meeting hydraulic data required for column sizing and rating. So click generate to run the simulation and calculate this data, and click cancel to manually run the simulation later. So we are going to click on generate. So over here the tray hydraulics is given to us. Let me just reduce the size of this. Okay, so over here we are going to add new. So a new section name has come as CS1. So the starting is going to be from the second stage to the 17th stage. That our first stage is our reflux drum, and our last stage is the reboiler. So this we are going to start at second, and we are going to end at 17. And once we just click outside, you can see that the tray spacing or packed height and the diameter is given to us. These are all standard values that Aspen has, that is inbuilt in Aspen. Now, once we have done that, it is said that the input is changed. So what we are going to do is we are going to run the simulation again. So you can see that results are available now. Another thing that we have to do is we are going to come to profile. Now you can see that apart from this hydraulics is also given. So the flow rate across each stage is also available to us now. What we are going to do next is we are going to, that is ninth stage is our feed stage. Initially what we had done is we have given a pressure drop of 3 bar across this control valve. So the pressure, the initial feed pressure was 6 bar, then there was a pressure drop of 3 bar, so this is coming at 3 bar. But from the simulation we can see that at the feed stage the pressure is around 1.23 bars. So what we are going to do is we are going to copy this value. We are going to come to this CV1, that is this control valve, and we are going to fix the outlet pressure as this pressure. Now you can see that the input is changed. Again what we are going to do is we are going to run the simulation. Now the results are available again. Our next step, what we are going to do is we are going to initiate the dynamics of this column. So for initiating the dynamics, we have to select this dynamic tab over here and select the dynamic mode. Now you can see that required input is incomplete because more specifications has to be given. Now you can see this red mark has come over this dynamics. We are going to select dynamics. Once we go over here, we can see that in reflux drum it is required that we need to enter the length and diameter of the reflux drum sum, that is the bottom of the distillation column or the 17th stage. Over there also we need to give the height and diameter of the sum, and similarly we have to specify the hydraulics of the uh, entire column. So how are we going to do that? For that we need the steady state profiles that we have generated in the simulation. So coming to profiles, we are going to go to hydraulics first. So over here, this is the volume of liquid flow. We are going to convert this into cubic per minute. So this is the first stage. First stage is our reflux drum, right? So in the first stage, the flow rate of the reflux drum is 0.003. We need to note down this value. Similarly, The flow rate at our 17th stage is 0.002. We need to perform calculation over here. So let me add a slide. Calculation for the length and diameter of the reflux drum. So what is the values that we have? The liquid flow rate from the reflux drum is 0.003 meter cube per minute. We have to take an assumption that the liquid hold up time is 10 minutes. This is an assumption that we have taken for our dynamics. Now let's come to the calculation part. Liquid hold up time is 10 minutes for the full volume. That is, if we are not removing the liquid for 10 minutes, then the reflux drum is going to be completely filled. So therefore we have V is equals to 0.003. This is meter cube per minute multiplied by 10 minute. This will give us 0.03 meter cube. This is the volume of the reflux drum. Okay, now we know that this is assumption number 1. Then assumption number 2 is the reflux drum is cylindrical in shape. Therefore, this V will be equal to pi by 4 into d square into L. I hope this is clear. This is from the volume of cylinder. Here D and L is the length and is the diameter and length of the reflux drum. Our third assumption is L by D, that is the ratio of length by diameter, is equal to 2. So this equation, it changes to 0.03, which is the volume of the reflux drum. This is equals to pi by 4 d square into 2d. This is from this relation over here. The length is being substituted as twice the diameter. So on calculating d from here, we are going to get d cube as 0.03 into 2 divided by pi. So d will be equal to 0.26 meter. Let's check it once. This to the power of cube root, that is 1 by 3. Yes, it is 0.267. So we are going to, since we are taking up to 3 digits, up to 2 digits, we are going to take it 0.26 meter only. So if d is 0.26 meter, so L becomes 0.53 meter. Or let us keep it as 5.2. Twice of the length is going to be the twice of diameter. So this becomes our the entire calculation for the reflux drum. So let us use these values over here. So in reflux drum, the length is 0.52 meter and diameter is 0.26 meter. Okay. Now similarly, we have to calculate the sump length and diameter. So for that, we have to come back over here, come to the profiles. Over here, the sump is as 0.002 meter cube per minute. Okay. Over here, the first and diameter of the sump. So the liquid flow rate of the from the sump is 0.002 meter cube per minute. The liquid hold up time is 10 minutes. this relation is not needed. The sump is also cylindrical in shape, and uh, we have to note that the diameter of the column is 0.13 meter. From where am I getting this? I am getting this from here. If we come to the setup, and we have already made this, so over here you can see that the diameter value is given. We are just, for ease of calculation, we are just taking 0.13. If you want, you can take all the digits for all the calculations, and you are going to get much more precise answer, but I am going to just go ahead with 0.13 meter as of now. So this is given to us. So the volume is going to change. This is 0.002 meter cube per minute into 10 minutes. This becomes 0.02 meter cube. Therefore, V uh, this equation remains the same. From the volume of the cylinder of the, this becomes, from the reflux drum, this becomes the sum of the column. This becomes 0.02. This is 0.13 square, and this is L. So from here we have to calculate the length. The length of the sum is going to come approximately around 1.5 meter. So for here this is 0.13 meter, and this is length is 1.5 meter. Okay, so we are going to put these values over here. Height is 1.5 meter, and the diameter is 0.13 meter. Okay, now coming to the hydraulics part. This is from second stage to the 18th stage. Sorry, this is for 17th stage. This diameter also has to be changed to the diameter that we are going ahead with the calculation. So this becomes 0.13 meter as well. No other changes are made in this. Now with all the changes we have made, we are going to click on next to rerun the simulation. So now this is done. Now coming to the dynamics part, we are going to select this. It is said that the flow sheet is configured to be fully pressure driven. Now we are going to go ahead with the controller part. We are going to click on OK. Now over here we are going to select pressure driven. Now a dialog box appears. We have to give a name to this file. So where am I going to save it? You have to select a location to save this file. And the file name I'm going to give as problem 2 dynamics. Okay, and then I'm going to click this as save. It is going to give us this message, but no need to worry. So this is the Aspen Dynamics version 12 file and the window, and this is how it looks like. So you can see that the flow sheet that we had made over here it just got imported, and it not only got imported, it got imported with all the steady state values that we have done the simulation with. Let us just save the this file first. Let us rename as problem to steady state. Now this is how a controller looks like. We have one pressure controller over here. Now we first need to change this to initialization. Okay. Now we have to see what all controllers we have to give over here. So first is we need to control the flow rate of the feed. So for that we are going to select this over here, and we are placing one controller. So this becomes B1. Let us rename this as this is a controller, right? So let us rename this as C1. This is a flow controller. So let us rename this as FC. Over here also we have streams. So this is a control signal. So once we come over here, you can see that these arrows are coming. So once we select this arrow, it is going to ask us what is the description that we want to control. So we want to control the total mass flow. So over here we are going to select this. I hope the screen is visible. So over here it is given total mass flow, this. So I'm going to select this, I'm going to click on OK. It is going to come over here. Over here this is a process variable. We are going to click on OK. Then this output that is coming over here, this is the controller output. We are going to click on OK. This is going to come inside the valve. This is the control valve over here. So what is this flow controller doing? It is going to check the flow rate and then adjust this control valve. Okay. Now our next objective is to control the liquid level in the deflux drum. So how are we going to do that? We are going to give another controller over here. Let us add the temperature control first. So this is a temperature controller. Just let us rename this. This is temperature controller. So from here we have to, it is given that the pressure is controlled. Sorry. We have to control the pressure of the column by regulating the deboiler duty. So for that, over here the stage is given. So the sump is stage 17. So we have to select this temperature. We are going to click on OK. It's going to come over here. This is a process variable, and the output, controller output, is going to go into the reboiler. So what we are going to do, we are going to control the reboiler heat duty. We're going to click on OK. So this circuit gets completed. This part is shifted over here. So this is the temperature controller. What all we need to do, this is done, this is done. So we need to fix the reflux flow rate. Also, I forgot to mention, we need to add a dead time to this controller. So over here we are adding one dead time. We connect the destination. This comes over here. This goes to here. And we are going to specify the dead time. The value of dead time that we are going to specify is 0.8 minutes. Next is we need to control the level of the reflux drum and the reboiler. So let me add one over here and another controller over here. Let me rename this as LC1 and LC. Right. Now for control signals, so we have over here. So what I have to control, I have to so this is stage 1. So we are going to control the liquid level of stage 1. So I'm going to select this. I'm going to insert it into this controller. The output of this controller output is coming to this control valve 2. Similarly, for this, it is going to be at the bottom. So this is stage 18 level. I'm going to click on OK. This is going to come over here, and this output is going to come over here. So this is done. One last step is left, that is we need to fix the reflux ratio, that is 2. So for that we are going to select this unit, multiply. Let me place this over here. And how are we going to fix this? Over here it is given that the reflux flow rate is fixed. So we are going to use this multiply model. Control signals. this. So this is you have to fix the total mass flow. This comes over here. The output of this will go here, and this we have to specify the reflux, that is specify total mass flow. And then I have to click it on OK. And this is done. This comes down. This goes down. This is S2. Now for this, let us rename this as reflux ratio fixed. And so forms all variables. This input 2, we are going to fix it as 2. Okay. So now almost everything is complete. Few more changes have to be made, like this flow controller. This flow controller, we are going to go to the configuration page. Over here, initially all these values are given as guess values. Now the control action is going to be reverse for this flow controller. Okay, we are going to select initialize variables. For this I'm going to click close. Similarly, for the temperature controller, we are going to come to configure, and all of these you can see these are PID controllers. Same over here also we are going to select reverse. We are going to initialize variables. The reason for choosing reverse action is because as the heat increases, the reboiler heat has to be reduced. The level controllers, they are proportional controllers. So selecting this, coming to the configuration page, the gain we can keep the same, but the integral time has to be increased to a high value since they are proportional controllers. And we are going to keep the control action as direct. So this is our level controller 1. Next is our level controller 2. This is our level controller 2. Going to the configuration page, we are keeping this the same and we are giving a high integral value. And this also, this is our level controller 2. We are keeping it over here. So over here our 4 controllers are given, and this is our 5th controller. This is also a proportional controller. So this is reverse. It is already, if you remember, we did not add this controller. It had come as we had generated this dynamics page initially. So now this is done. We are going to change this mode into dynamic, and now we are going to run the simulation. So over here you can see that all the values are changing. For 100, there is some error in the flow sheet that is happening. So tomorrow also we are going to have a class. I am going to discuss this problem again tomorrow. I need to recheck the simulation again, and I'm going to let you know the problem that is occurring over here. We are going to start this problem afresh from tomorrow, in tomorrow's class, and we are going to solve a few more problems on Aspen dynamics. So if there aren't any doubts, then I would end the class today.
No, sir, nothing, sir.
Thank you.
Yeah, thank you, sir.